Welcome again to heat transfer subject. In this session, we are going to continue our discussion about the introduction and some basics of the heat transfer. In previous session, you have seen what we mean from heat transfer, and we have also started to write some equations and energy balance or thermal energy balance actually for different systems. We have seen different type of system, open system and closed system, and also some equations. Now we are going to continue our discussion about energy balance and for some other special cases. One of them is surface energy balance. Why it is important? Usually the heat transfer is occurring on the surface. And if we can find a relationship or if we can write energy balance for the surface, it's our calculation equation will be much easier. Why we have this special case? If you remember, we had this equation, heat generation, this equation Q in minus Q out plus E generated equal to delta E thermal of the system. But when we have a surface, based on the definition which we have for a surface doesn't mass, doesn't any volume, and its thickness can be neglected. So because it doesn't have any mass and also the volume, so heat also cannot be generated on the surface. And our equation, our surface energy balance equation will be like this. E dot in will be equal to E dot out. Like what you can see here, we have a wall on its surface. For example, if by conduction, the Q dot 1 is transferred from wall to the surface, then it is the heat transfer from the wall to the surrounding by radiation and convection will be the summation of these two will be equal to this one. Q dot 1 will be equal to Q dot 2 plus Q dot 3. Why we can write this equation? As I said, because we don't have any heat generation in the wall. So a surface contains no volume or mass, so it doesn't have any energy. So energy is not generated in that. In practice, we cannot have such a surface or with these properties, but we can assume which we have the surface with its properties. How about the directions? Direction is not important. We can write all of the equation, all of these heat transfer like this. Summation is that in equal to 0. In other words, we can assume all of the heat transfer are toward to the surface. After our calculation, you will see the heat transfer to the wall is Q in positive, and from the surface will be negative side. So the surface is important, and what you need to know about the surface heat transfer is we don't have any energy on the surface, and we can write this equation for the surface. Now here we have an interesting example, and you will see when we say control volume, when we say flow, it is not only for the fluid, and we can use that concept to solve some other problems. Here what we have is a stainless steel sheet. It is heated, the temperature is 500 degree Kelvin, and it will go through a cooling chamber or something like a cooling chamber, and its temperature will drop to 300 Kelvin. So imagine we have a sheet, it is moving, and its initial temperature before the cooling chamber is 500. After that will be 300 Kelvin. So we have a stainless steel sheet. It is baked on weight at a constant speed of 1 centimeter per second. So it's moving with 1 centimeter per second into a chamber to be cooled. The stainless steel sheet is 5 millimeter thick. We know the thickness of the sheet. And also the width of the sheet is given, which is 2 meters. And it enters and exits the chamber at 500 at 300 Kelvin, as I said. Now we need to determine the rate of heat loss from the stainless steel sheet inside the chamber. Again here, we can write this word, heat loss. Why? Because you can see the initial temperature of the sheet is 500 Kelvin, and the final temperature is 300 Kelvin. So it means the temperature is dropped and we have heat loss from the sheet. Now again, we need to have good assumption. First of all, we need to imagine a steady operating condition exists. And here, one interesting thing about this, however, this is not a fluid, but we have the flow of a stainless steel sheet. So we can discuss about this sheet, or we can look at this sheet as a control volume or a flow of the sheet. First assumption, a steady operating condition exists. We need to have this assumption for most of the problem related to the steady flow. The stainless steel sheet has constant properties. You need to have this because we will work with the average heat transfer here. And changes in potential kinetic energy are negligible. As I said this morning, they are small compared to the change in the energy of the system due to the heat transfer. Okay, now we are going to calculate heat loss or heat transfer from this Q dot loss. How we can calculate that? As I said, we can select our control volume like this. Okay, imagine part of this, uh, a part of this sheet, we select that as our control volume. So from this part, it will enter, you know, uh, the sheet will enter to our control volume, and from this side will goes out. Or we can say we have a flow of the sheet in this control volume. If you remember, this is a open system, and we have a control volume. And if you remember, to calculate heat transfer or rate of heat transfer for such a system or control volume, we use this equation Q dot, which is Q dot last year actually, is equal to m dot Cp T in minus T out. And why we write T in minus T out? Because T in here is higher than T out. It lasts. Usually we have T2 minus T1, but here it is heat loss. If we write T out minus T in, everything is same. Only the value will be negative. Here you can write like this to calculate the value, which Q dot loss is 81.4 kilowatts. I will go to the parameters. And the value is 81.4 kilowatts. It is loss, so we know it is negative, kind of sense of negative value. Okay, so we need to use this equation, Q dot loss and that Cp T in minus T out. We have T in, we have T out as a temperature difference. How about m dot and Cp? What is m dot? M dot is mass flow rate to our control volume. How we can calculate that? How much mass is coming to our control volume? How we can calculate that? And that is equal to, first of all, density of the material or substance which is in our control volume, and times the volume flow rate. This VWT actually is volume flow rate. You know, this equation is m dot rho v dot. Rho is density of this substance, which is stainless steel. It is noun, and we can find it from the table in the textbook. Actually, as I said, I will show you these properties from different tables. From table A3, you can find density for the stainless steel. In the final exam, midterm exam, or even in the quiz, these properties like density or other type of these, I should give you table for that, or I will, or you need to refer to your textbook. So the density from this table, from textbook table H3 for stainless steel is 7,900 kilogram per meter cube. And why volume flow rate is this? You know, W is the width of this sheet, and T is the thickness of that. And if we calculate, WT is AC, or the cross section, and this cross section times V, or velocity of the sheet, will give us the volume flow rate. So by this equation, we can calculate mass flow rate. Rho, we have 7,900. V, or velocity, we have, it is given 1 centimeter per second. We convert to the meter per second. Time the width is 2 meter, and the thickness of the sheet. Finally, m dot, or mass flow rate, will be 0.79 kilogram per second. Okay, so we already have the m dot, T in, and T out. How about CP? As I told you, for CP, or a specific heat for different substances, we need to refer to the tables which we have. And as I told you, I will show you the table. So you need to go to the tables. In those tables, we have something like this. For example, CP. And for a substance, for example, here we have a stainless steel for different temperature. If you remember from thermodynamics, we had these, for example, 10 degrees Celsius, 20 degrees Celsius, and CP, joule kilogram per Kelvin. Okay, for 10, 20, 30, and so on. We have CP. For example, here, 515 for the 400 Kelvin temperature. Is 550. 400. Why 400? We have 500 and 300 here. But if you remember, in the equation which we have here, we also mentioned in earlier slides, I think we had that, we need to use CP for average temperature, or CP average. Okay, so CP should be for average temperature. The temperature which we have here is 500 and 300. What will be the average temperature? 500 plus 300 divided by 2 is 400 Kelvin. So average temperature for this control volume is 400 Kelvin. And CP for stainless steel at this temperature is 515 joule per kilogram Kelvin. So we have also CP. Q dot loss for this sheet of stainless steel in this cooling chamber can be calculated by this equation. We have M dot, we have CP, we have T in, T out, and finally Q dot loss is 81.4. If we do not mention loss, Q dot will be equal T out minus T in, and this will be negative sign. And by this also we can understand we have heat loss during this heat transfer process. Okay, any question about this example? Okay, I hope it is clear. A little complicated, but what is important in this example is you need to know that the control volume is not only for the flow; it can be used for any substance which has some kind of the flow. Okay, so we have finished the energy balance. Now we can go to the heat transfer mechanism. I think you have already know about this from your schools, so I will just review these three modes of the heat transfer. Uh, as I told you, in the morning session, heat is transferred due to the temperature difference from the body with higher temperature to the lower temperature. And we have three modes of the heat transfer: conduction, convection, and radiation. The, uh, the common properties for these three types of the heat transfer is the requirement for a heat temperature difference or temperature difference between two media. First, let's talk about the conduction as the most common type of the heat transfer. In the conduction heat transfer, the energy transfer from the more energetic particles to the adjacent less energetic particles uh, is the reason for this type of the heat transfer. In other words, uh, energy is transferring from one molecule, I can say, to the other molecule one by one. And we need to have a substance for this type of the heat transfer. It is most common type of the heat transfer, like the heat transfer inside the wall, inside different type of the solid materials, or even liquid material or gases without motion. When the liquid is not in motion, also we have conduction. And the rate of heat conduction for is is dependent or proportional to some property. It is proportional to the temperature difference across the layer T1 and T2, and also the heat transfer area, the area which heat is transferred through that. But it is inversely proportional to the thickness of the layer. In other words, as much as the thickness of the substance is higher, the heat transfer is lower from one side to the other side of that substance. So we can write this equality sign. Rate of heat conduction is a function of area and temperature difference, and it is inversely proportional to the thickness. Based on this finding, an equation is developed by Fourier, and it is like this: Q dot conduction or rate heat transfer rate by conduction is equal to Ka T1 minus T2 divided by delta X. What is T1, T2? Temperature at uh, the first surface and the last surface, or 2 points actually of the substance. Imagine this is a plane wall with a thickness of delta X. Then Q dot conduction for this plane wall is like T1 minus T2. What is delta X? Is the thickness of the heat transfer. What about K and A? A, as I said here, is the area, this area. This area, which we cannot see that, the area normal to the direction of the heat transfer. How about K? K is the constant which we call the thermal conductivity. It is the properties of the substance. And for different substances, we have different value of the thermal conductivity. Generally, it depends on the crystal form or the microstructure form of the substance. And later we will discuss about K, and we will see for different substances how is it. But what you need to know from this slide is this equation: Fourier law of heat conduction, Q dot conduction is equal to negative Ka dt by Tx. Here we have a negative sign. Why we have negative sign? Imagine we don't have this negative sign. Then K is a positive. K is always positive. It is the value of heat transfer. A is the surface cross section, so it is positive. How about dt divided by dt, dx, or t. Actually, this is t1 minus t2. Uh, t1 minus t2 is positive. If we write our equation like this, it is okay. Q dot will be a positive value. K is positive, A is positive, T1 is bigger than T2. The result of this will be a positive. Delta X also is positive. Finally, the Q dot will be positive as well, which is right. But if we write delta T means T2 minus T1. This is delta T. So T2 minus T1 is negative because T2 is less than T1. So when we write this equation like this, instead of T1 minus T2, we write delta T. Because delta T is negative, so we need to have this negative sign before that to make the total value of this positive. This is the reason why we have this negative sign. And if we imagine instead of delta H, we have some element or very small thickness of the wall, then we can write dt in the differential form, dt divided by dx. This is an important equation, especially in chapter 2. We will more work on this equation for different heat transfer systems. About thermal conductivity, as I told you, it is a properties of the substance, and it shows the ability of material to conduct heat. And for different material, it is given, like what you can see here. We will wish that. And dt dx, which we have here, is temperature gradient, which is the slope of the temperature curve on Tx diagram. In other words, is this one. The slope of this line is the dt dx. About thermal conductivity, or K, very important parameters in heat transfer. You will see this parameter in all of the problem which we have conduction. The rate of heat transfer through unit thickness of the material per unit area per unit temperature difference is the definition of K, actually, which determines its unit as well. Kelvin, watt per meter degree, Celsius, actually. This is the value or the unit, actually, of the thermal conductivity for different substances. And if you notice here, we have, for example, different substances here: diamond, silver, copper, for the water, for the fluid as well, for the gases. And what is interesting about the value of the thermal conductivity is for pure crystals and metals, the thermal conductivity is much higher. Like diamond, we have highest or maximum thermal conductivity. And as much as the crystal, the shape of the crystal is changed and until we reach the metals, this thermal conductivity is reduced. And the lowest thermal conductivity is for different type of the gases, as you can see here. And so for insulation, we use gases. If you know, we have, in some cases, we use air as an insulator. We have a gap between two, for example, glasses for the windows because of its insulation properties. But if you know, in the our laptop, in our phone, there is gold. Why we have gold in the circuit of the different electrical equipment? Because its thermal conductivity is high, its thermal resistance is low, and the temperature is not increased in that substances during heat transfer. So thermal conductivity is important property of the material. It shows how a substance can transfer heat and or temperature. And it is mentioned here, the high value for thermal conductivity, it means it is good to be used as a heat conductor, and the low value of thermal conductivity means that substance is good to be an insulator. But the thermal conductivity of the substance is also dependent on the temperature of the substance. In some of the examples, we need to assume that the thermal conductivity of substance remain constant during that heat transfer process. But in real application, and when the temperature difference is too high or too much, then we need to also include the change in the thermal conductivity with change in the temperature. You can see here different graphs. For example, you can see for diamond, when temperature is 200 Kelvin, the K is this much. But with increase of the temperature, the thermal conductivity is reduced. And for some material, when temperature is increased, thermal conductivity is decreased. But for some material, like this one, you can see when the temperature is increased, thermal conductivity is also increased. All of these values are measured experimentally. For helium, for example, by increase of the temperature, the thermal conductivity is increased. Generally, for the gases, as you can see here, by increasing the temperature, thermal conductivity is almost increased. But for the solids and some of the liquids, with increase in the temperature, the thermal conductivity is reduced. But you need to be careful when how much is the temperature difference during that heat transfer process. In the previous example, it was 100 degree, 200 degrees Celsius change in the temperature. So thermal conductivity, how much has changed? We need to check that if we can assume that thermal conductivity is constant during that heat transfer process or not. For example, for the copper and aluminum, you can see in different temperature, we have different thermal conductivity for this substance. For copper at 100 degree, 100 Kelvin, the thermal conductivity is 482, and in the 200 Kelvin, its thermal conductivity is 430. And for example, in this range, you can see how much the thermal conductivity is different. More than almost 70 watt per meter Kelvin is difference in the thermal conductivity. So if the temperature for the copper, for example, is changed by 100, it means from 100 to 200 degrees Celsius, then maybe we cannot assume that the thermal conductivity remain constant. If we assume that thermal conductivity remain constant, then, for example, use this equation to calculate the conduction heat transfer rate, then what happens is the error in our calculation will be higher, will increase. And in those cases, we need to use variable thermal conductivity. This is also a topic for next chapter. We will go more detailed about that in next chapter. The other modes of the heat transfer is convection. In the conduction, I said the heat is transferred due to the energy transfer from more energetic particles, which are molecules, to the close or adjacent molecules. How about convection? Convection is the heat transfer between a solid surface. This word is important. We need to have a solid and the adjacent liquid or gas that is in motion. All of these red lines or red words are important. Convection is only happen if we have a liquid, a fluid actually, liquid or gas in motion. This word is important. For example, if we have a bottle of can a can actually inside water, but the water is not in motion. We have only conduction in the water or even in the can or from the surface of the can. We don't have convection. So convection needs motion of the fluid. Like this example, imagine we have a hot block. The air is blowing or flowing on the surface of this solid. Then heat is transferred by convection from the surface to the fluid or vice versa. Depends on the temperature. But usually the heat transfer is from the hot block or from the solid surface uh, to the fluid. So, and the faster the fluid motion, the greater the convection heat transfer. This is the reason why we have fan in our laptop, in our houses. We have fan because it will cause the motion of the air. Air is a fluid. Then it will contact with solid surface like our body, like walls and so on, and heat is transferred from the wall, which is in higher temperature, to the air in the motion. This is convection heat transfer, and the motion of higher motion means higher convection rate. And it is like this. Imagine we have air flowing through a surface of a hot block. The velocity of the air on the surface, when it is exactly on the surface, is assumed to be zero. And as much as it is enough far from the surface, it's assumed to reach a constant velocity equal to V. How about the temperature of the fluid flowing above the surface? The temperature at the surface of the solid and the fluid, which they are in contact, is assumed to be Ts. Ts is the temperature of the surface. And the temperature of the air or the fluid above that, if we go far from the surface, will be equal to the temperature of the surrounding. So this is why this heat transfer happen, because we have heat temperature difference, Ts, T infinity, which is T of the environment. By this, temperature will reduce. Heat is transferred like this, Ts and T. Here in the conduction, we had like this, T1, T2. Here we have Ts, T infinity or environment. This is convection heat transfer, and we have two methods of the convection heat transfer. Natural convection heat transfer, like a hot egg, which is in the on the table without any fan. Then the natural convection is happening due to the change in the density of the air. As you know, if the temperature of the air or any other type of the gases is changed, its volume also will change. Changing in the volume or will cause the change in the density of that gas. Then here, the air around the egg, its temperature will increase, density will reduce because volume is increased. Then this gas will go up, and the gas which is here, which its density is higher, will come to down. And this circulation is always happen. This is natural convection, and we will discuss about that in chapter 3. And also we have forced convection when we add a fan like this. As I said, if the motion of the fluid or the fluid flow is increased, then the convection heat transfer rate is increased. So this is the reason why we have fan, because we are going to increase the convection heat transfer. And the other type of the convection heat transfer is the heat transfer due to the change of the phase. For example, when you use ice inside the water to cool down the water. We have phase change process here. This type of the heat transfer is also included in the convection heat transfer because it is in the motion. You know, we have some kind of the motion as the solid, the ice is melting. Some liquid is, some droplet is will form and will separate it from the ice. So we have motion of the fluid, and that kind of the heat transfer also is uh, convection heat transfer, and it is really high value of the heat transfer. Because of that, the ice is an effective way. Adding ice to the water is very effective way to cooling down the water. And also the other type of the phase change process. How we can write equation for this type of the heat transfer? As I said, again, we have that temperature difference. Ts minus T infinity. T infinity is temperature of the surrounding enough far from the surface. Why enough far from the surface? Because, for example, here the temperature is T, which is equal to T infinity. Here also T infinity. In other words, when we reach a distance from the surface, which the temperature remain constant in that surface, we call that enough far from the surface. So we have Ts, temperature of the surface, T infinity, temperature of the environment. We have As, which is the surface, you know, the surface which we cannot see on this direction of the view. The surface which heat transfer is occurring through that as the uh, area or surface of the convection heat transfer. And we have a new parameter here, convection heat transfer coefficient, which its unit is watt per meter squared times degree Celsius. Very important parameter. And we usually, for convection, we need to find this. The question in convection heat transfer is mainly related to H. We need to find H usually. You will see also in the examples. And I told you about AS, TS, and T infinity. And you can see the H or the convection transfer coefficient, how changes with the change in the mode of the heat convection heat transfer. It is forced or natural and for different surfaces. For example, free convection of the gases, the H is 225, and free convection of the liquid is higher. Forced convection, you know, if we add a fan, you can see it is multiplied by 10. And forced convection of the liquid, you can see how much it is increased. So adding just a small fan, how much can increase the convection heat transfer coefficient. Because of that, we add that. And boiling and condensation, as I told you, the condensation as the one type of the convection heat transfer. And you can see the maximum, 2,500 and 100,000. Very, very big numbers for the convection heat transfer coefficient. And you will see in the different examples how much this is important. And as I told you, in different examples, we usually are interested to measure these or to calculate this H or the convection heat transfer coefficient. Imagine we have a wire like what you can see here. We have a 2-meter long, 0.3 centimeter diameter electrical wire, extends across a room at 50 degrees Celsius, like what you can see here. Which is generated in the wire as a result of the resistance heating. The surface temperature of the wire is measured to be 152. So Ts is 152. The temperature of the surrounding is 15 degrees Celsius. Also, the voltage drop and electric current through the wire are measured to be 60 volt and 1.5 ampere. Now, disregarding heat transfer by radiation, later we will discuss about that. Now we need to determine the convection heat transfer coefficient for heat transfer between the outer surface of this wire and the air in the room. How much is the H? Okay, again, we'll start with assumption. A steady operating condition exists, nothing changed with time. 2, radiation heat transfer is negligible because it is also mentioned in question instruction. Okay, when we have a steady operating condition, the rate of the heat loss from the wire will be equal to the heat generation in the wire. Why? Because it says we have a steady operating condition. The temperature doesn't change with time for the wire or surrounding, none of them. So it means the temperature which is generated inside the wire is transferred to the surrounding in a constant rate. In other words, Q dot, which is the amount of the heat transfer, equal to E dot generated. If we don't have this equality, it means temperature of the surface of this wire should increase because some of the heat is not transferred to the surrounding. If Q dot is not equal to E dot generated, temperature will not remain constant. But because it remains constant, then it is equal. Q dot will be equal to E dot generated. E dot generated, or amount of the energy or thermal energy which is generated in the wire, is due to the flow of the electricity. From the physics, you know that this amount of the energy is equal to V times I, which V is the voltage and I is the current of the electricity. You need to know this from the physics. So it is given 60 volts. It is given the current 1.5 ampere. So finally, the Q dot for the heat transfer rate will be 90 watts. How about, to calculate the H in this example, because we have convection, heat is transferred to the air in the surrounding of this wire due to by convection. So we need to use this equation, and it is mentioned that we need to calculate H. H equal to Q dot convection divided by AS times TS minus T infinity. We have TS 152, the temperature of the solid surface. We have T infinity, temperature of the surrounding. And Q dot convection, we have calculated here amount of the Q dot, which is the heat transfer to the surrounding from the surface. How about the AS? We assume that the heat transfer in the whole surface of this wire is constant or it is steady. So we need to calculate the whole surface of this solid, which is a cylinder actually. And the surface of a cylinder can be calculated by this equation, pi dl. Pi, d is the diameter of this cylinder, or this wire actually here, which is 0.3 centimeter, and the length of the cylinder or this wire actually is 2 meters. So conversion to the meter is diameter, and 2 meters is the length of that. Finally, we can calculate AS as the surface area for the convection heat transfer. If we put all of these calculations, so now we have AS. Q dot convection we have calculated, TS, infinity, we have all of them. If we put in this equation, we can calculate H, which is equal to 34.9 watt per meter square Kelvin. And actually, this is the method, we call that hot wire. If you are interested about the heat transfer science, you can continue your further study about hot wire technique to measure these H or convection heat transfer coefficient. This is one method to measure convection heat transfer for different substances and in different conditions.